Hi everyone, this is Anushka and welcome back to my channel A in Economist. So in the previous few videos, we have talked about what is specification error and specification bias. Specifically, we have gone into these 5 kinds of specification error that you can see on my screen. And in that, we have talked about what will be the effects of omission of relevant variables, what will be the consequence of omission of a relevant variable from your regression model in details in the previous 2 videos, right? I have uploaded a 2-part video. There I have explained the concept of omission of relevant variable, and also I have listed down and I have also proved all the consequences of omission of relevant variable. If you haven't watched that video, please check that out. So today what we will going to do, we will go into the next specification error, next kind of specification error, which is known as inclusion of unnecessary variables. So again, we will do the same thing. We will understand the concept with the help of models, and then we will go into the detailed proof of the consequences, right? So let's get started with that. So see, inclusion of unnecessary variable is also known as overfitting of model. So we are now talking about overfitting of the model. So these two terms can be, alternatively used. Inclusion of unnecessary variable means overfitting of the model, and omission of relevant variable means underfitting of the model, right? Please remember this thing. Now let us look at the models that we are using. So the true model, here I have written this for you. True model looks like this: yi equals to beta 1 plus beta 2 x2i plus ui. Let me call it model number 1. Here, as you can see, here you have only one dependent variable, only one outcome variable, and only one explanatory variable in your model. So the true model is this. So basically, as a researcher, as an econometrician, you should go with this kind of model in your particular situation. But due to some mistake, due to your lack of knowledge or lack of data, whatever you have overfitted the model. You have included one unnecessary variable in your model. See here you have only one outcome variable that is the same as the true model, but you have two explanatory variables. Ideally, you should have used only one explanatory variable, which is x2, but due to some mistake, you have included x2, also x3. This is an extra variable that you have added in your model. This is the incorrect model, right? Let me call this model as model number 2. This is basically overfitted model, means this is an incorrect model. Incorrect model that you are using for your analysis, right? So here the specification bias, or the specification bias will arise due to inclusion, of this unnecessary variable, namely x3i. Now, how do you check that it is necessary or unnecessary variable? That will be checked using this coefficient of it, alpha 3. Suppose you are doing an hypothesis testing, alpha 3 equals to 0, versus alternative hypothesis is alpha 3 not equals to 0, and using the sample at 5% or 1% level of significance, you find that you fail to reject the null hypothesis, that you accept this null hypothesis, which means alpha 3 is exactly equals to 0, which means x3i is not a statistically significant variable, right? If this is the case, then you can say that yes, x3 is an unnecessary variable and it is not explaining any sort of variation in the outcome variable yi. That is why it is an unnecessary variable, and here the specification bias will arise due to inclusion of this unnecessary variable x3, right? So this is just the opposite of what we have done in the previous video, that is the omission of variable. In case of omission, these two models were interchanged. This model was the true model and model was the underfitted model, right? I hope you can relate this thing. Now, if this situation is arising, then what will be the consequence in your study? So for that, see, I have listed all the consequences here. So remember one thing, the consequences of the inclusion of unnecessary variables will be less severe, than the consequences that we have talked about in the omission of relevant variable. So omission of relevant variable is a more severe kind of a problem with respect to relative to the inclusion of unnecessary variables. So ideally, both the specification barriers biases should not be present in your model, but if it is present, inclusion of unnecessary variable will be less severe. The consequences will be less severe than the omission of relevant variables. Right now, let us see what will be the consequences. The first consequence is the OLS estimators of the parameter of model 2. Model 2 means the overfitted model, the incorrect model, will be unbiased as well as consistent. So biasness will not arise. This is a major, contradiction to the previous specification error. We have seen that in that case, the estimators were biased and inconsistent. But as I've told you, this consequences will be less severe. Here, the unbiasedness and the consistency is holding true. So symbolically, what you will say, expectation of alpha 1 cap will be exactly equals to beta 1. Expectation of alpha 2 cap will be exactly equals to beta 2, and expectation of alpha 3 cap. Can you tell me what will be this value from this model? Let me remove the writing. You can look at this and try to observe. Pause the video and think what will be expectation of alpha 3 cap. Expectation of alpha 3 cap will be simply 0. So unbiasedness means alpha 1 cap is correctly estimating the true population parameter beta 1. Alpha 2 cap is fully capturing the true population parameter beta 2, but corresponding to alpha 3, you do not have any beta 3. So expectation of alpha 3 cap will be simply equals to 0. So these three criteria will hold, and this will also hold when n is tending towards infinity. So consistency means what? If you increase the sample size, if your sample size is going towards infinity, then all the expected values will go towards the true population parameters. If this is the case, then you will say consistency also holds. So here we can see OLS estimators will be both unbiased and they will be also consistent estimators of the true population parameter. If here it is not equals to 0, then biasness would have arisen. Right? If this is not equals to 0, biasness would have arisen. If this is not equals to beta 2, biasness would have arisen. If it is not equals to beta 1, then biasness would have arisen, but this will not be the case here, and we will prove this. We will prove this in this video, then we will see, right? So this is the first consequence. The next consequence is the error variance of sigma square is correctly estimated and it is correctly specified. So basically sigma cap square, this is the estimator, this is the unbiased, this is the estimator, and this will remain unbiased. This will remain unbiased if you include an unnecessary variable in your model. The third consequence, the confidence interval hypothesis testing procedure will remain valid. These are also, contradictions to the previous specification error. In the previous omission case, in the underfitting case, we have seen that error variance is not correctly estimated. Also, confidence interval hypothesis testing was not valid there. So that is why these consequences are less severe. The only negative consequence is this. The only negative consequence, which is a bad consequence, is this, that the estimated variance of alpha caps will be larger than those of the beta caps of the true model. So basically, the estimators will be inefficient in nature. The estimators, they will be consistent, they will be unbiased, but the only problem is that they will be inefficient in nature. That is one of the major drawbacks, right? This is not there, this was not present in case of omission case. In the omission case, the estimators were efficient as well, but here we will see that is not the case. So basically, variance of alpha caps will truly exceed the variance of beta caps. This we will also show. Right? I hope this explanation is clear to you. Now let us go into proving the consequences, right? Let us do the proof. Firstly, we will show the unbiasedness proof. So for the unbiasedness proof from the true model, what will be beta 2 cap? Look at the true model here. This is the true model. True model is a two variable simple classical linear regression model. So here what the and only explanatory variable is x2. So if it is the case, we have done this multiple times. What will be beta 2 cap? It will be I from 1 to n yi x to I upon summation I from 1 to n x to I square, right? This we have done multiple times. So I'm not, explaining this again. If you haven't watched my playlist on econometrics and advanced econometrics, please check that out. You will find this proof multiple times, right? So this is from the true model, and from the incorrect model, From the incorrect model, what can you say about alpha 2 cap? So let me again show you what is alpha 2 cap. Alpha 2 cap is a 3-variable model, 1 outcome variable and 2 explanatory variable. Basically, multiple linear regression model in 3-variable scenario. This estimator also we have derived in multiple ways before. Let me write it for you. I from 1 to n. First term was yi x to y. Then you have summation I from 1 to n. This will be x 2i square. Sorry, x 3i square. yi x 2i into x 3i square minus, this will be summation I from 1 to n, yi x 3i into summation x 2i x 3i upon summation x 2i square I from 1 to n, summation I from 1 to n x 3i square minus summation I from 1 to n x 2i x 3i and a whole square of that. So this will be the formula. I know it looks a little scary, but I have done the derivation before. If you have any problems in this, please check those videos out. I'll give the link in the description. Also in the I tab button, you will find the entire playlist, right? So please check those out. This will be the estimators. This is the estimator of beta 2. From the true model, this is the estimator of alpha 2. Alpha 2 is the corresponding estimator of beta 2 in the incorrect model. So now we have to find a way to compare between the two and take expectations. So what we will do, firstly, we will convert our true model into the deviation form. So the true model, that is the model number 1, looks like this. yi equals to beta 1 plus beta 2 x 2y plus ui. This is the simple model we have for all I from 1 to n. Now y bar will be what? Beta 1 plus beta 2 x 2 bar plus u bar. Now if you take the deviation yi minus y bar, this beta 1 will cancel out and you will be left with beta 2 x2i minus x2 bar plus ui minus u bar for all I. Now, as usual, what we do, we convert it into the deviation form. So deviation form means writing in the small letters. Small yi equals to capital yi minus capital y bar. So this is the deviation. This is again a deviation. This is small x2i, small x2i, and this will be as it is, ui minus u bar. So this is the true model in the deviation form, right? This is our true model in the deviation form. Now what we do, this is yi value, small yi value. Now what we will do, in this scary looking expression, wherever you see yi, wherever you see yi, see here you have a yi, here you have a yi, anywhere else? No. So here and here you have to replace this entire expression, right? Here you have only two expressions where you have yi, so denominator is independent, denominator will not change. Only in the numerator, wherever you have yi, please put that thing to convert the entire thing in terms of xi, basically xi and ui. So let us do that. I know the calculation will be a little heavy here, but stick with me. Alpha 2 cap, and some of you were asking me about the notes that I am using, the handwritten notes, the PDFs and the PPTs that I am using. If you want to take this PDFs with you can directly write me in the comment section and I'll think about it and I'll make a way for you to give away this PDFs, right? So I'm planning to sell this PDFs also. So if you want, you can drop me in the comment section that yes, I want this PDF. I will charge a very nominal fee and then I'll give this to you, right? So alpha 2 cap is what? See, x2i is as it is. Now instead of yi, write this entire expression that we derived. So beta 2 x2i plus ui minus u bar, and then summation I from 1 to n x3i square is there, minus, what do you have? Summation I from 1 to n. As of now, please write this with me, otherwise you don't get what I am doing, right? It's only the derivation. It's only derivation that you must do on your own. Otherwise, it will be difficult for you to understand this things. So summation I from 1 to n x2i, x3i, right? This is the numerator and the denominator will remain as it is. Summation. Okay, so instead of writing the denominator, let me write it to be a. Sum a. A is basically this entire denominator here. This will be exactly the same till the very end. So I'm not repeating this entire expression again. But once when you will derive it in your copy, please write the entire thing, right? Now what you can do, now in the numerator, you can do some simplifications. See, here you have beta 2 and here also you have beta 2. So take this beta 2 out from the expression. If you take this beta 2 out, you will be left with what? So from the first expression, see, this will be summation I from 1 to n x2i square. Here x2i, here you have x2i, so x2i square. And then multiplied with summation x3i square. This is there minus summation I from 1 to n. From here, what you will get summation x2i, and then you have x3i and a whole square of that. Can you see this? Can you observe this thing? See, here you have x2i and here you have x3i. So I am just taking beta 2 common from this expression and this expression. First term is this summation x2i square into x3i square here. And then from this expression, if you take beta 2i common, it will be x2i, x3i and a whole square of that. I hope this thing is clear to you. And then plus, if you take summation ui minus u bar common, then what you will be left with? You will be left with summation I from 1 to n x2i, and then you have summation I from 1 to n x3i square minus this is x3i summation I from 1 to n x2i x3i, and the denominator remains as it is, which is simply a, right? So this is, I know it's a scary looking expression, but see, I am just taking out terms and I am just rearranging them, right? If you do it on your own, you'll understand this. Now what you can see here is that this term, this entire term is exactly the same with a. Summation x2i square, summation x3i square minus summation x2i, x3i whole square. So let me show you this term here. This term is a, x3i square, x2i square into summation x2i, x3i whole square. So the same term is there. So up and down, you can cancel them out. So let me do that. It will be alpha 2 cap. So if you cancel out, you will be only left with beta 2. So beta 2 will be out and this term will cancel out with this a. So it will be simply beta 2 and the next term will be as it is. Summation I from 1 to n ui minus u bar and summation I from 1 to n x2i, I from 1 to n x3i square, x3i, and then summation x2i, x3i. And in the denominator of this entire expression, you will have this a term there. So basically, we have taken a on both the sides. We have individually taken a to the both terms to get this. Now simply what you will do, you will take expectation on both sides. Now we have reduced this entire term. So expectation of beta 2 will be beta 2. And now in the next term, expectation will be on only ui's. So expectation of ui minus u bar, and then the entire term will be there. This entire term in the xi format. So this will not get affected. Let me call this some d. This is some constant. Xi's are basically non-stochastic terms, and here you have a. A is also non-stochastic, B is also non-stochastic. So you can treat this as a constant. So alpha 2 cap will be simply equals to beta 2 and plus this term. By this time, I hope you know that expectation of ui minus u bar will be expectation of ui minus expectation of u bar. So both are individually 0. So this term will be 0. So this entire expression will come out to be 0. So there is no need to write this, and that is how you prove that alpha 2 cap is an unbiased estimator of the true population parameter beta. Right? So I have done this for alpha 2 cap, the similar thing, exactly the same thing you can prove this for alpha 3 cap. I am not doing this here. I'm giving you as your homework. Please try to prove that expectation of alpha 3 cap is equals to exactly 0 because beta 3 is not present. Beta 3 is not present. So this term will not be there in your derivation, the homework that you will do. Only, the rest of the terms will be present. That will come out to be 0 again. So in the expression, I'm giving you a hint that in the expression that we have, landed up here, every term where you have 2, in alpha 3 case, you will have 3 there. For 2, 2 will be replaced by 3 and 3 will be replaced by 2. Only this much will be the change. The rest of the every line that I have done here, every line will be exactly the same, right? So I don't want to waste time. So please do this as your homework and this will help you to understand the concepts, right? So here also see there is no n terms. N is not there. So for n tending to infinity, expectation of alpha to cap will still tend to beta 2. So the estimators, the first consequence we have proved that the estimators will not only be unbiased, they will also be consistent. So this proof is done. Now let us go to the second point. Error variance of sigma cap will be exactly estimated since the parameters are unbiased. Since the parameters, let me write it here. Since the parameters are unbiased, what we can write, sigma cap square, this will be simply equals to RSS by n minus 3. You have 3 parameters in the model, so it will be RSS by n minus 3 and this will be correct estimation. This will be correct estimation. So the RSS, both the RSS and the ESS are correctly estimated. That is why this estimation that you will find out, this will still be correct estimation. Now the third consequence is the confidence interval and hypothesis testing that depends on the variance. So let me show you here. Let me show you what will be the impact on variance. This will be the last thing. What will be the impact of variance? Basically, we want to show that the variances of the parameters will be inefficient. So how do you show that? Again, consider the variance of the incorrect model, parameters of the incorrect model first. So this will be sigma square summation I from 1 to n x2i square 1 minus r23 square. This we know. This we have done multiple times. So this is the variance of the estimator of the incorrect model. And what about the variance of the true model? This is a two variable simple linear regression model, CLRM model. So it will be simply sigma square upon summation x to y square. This is the true model or simple CLRM. This is the MLRM model and this is the CLRM model. Right? This is the variances we have proved multiple times. Now what you will do, simply take the ratio. You want to compare between these two, simply take the ratio variance of alpha to cap upon variance of beta to cap. If you do that, this sigma square will cancel out and you will be left with only R23 square, 1 upon 1 minus R23 square. Now, can you tell me what is R23 lie between? R23 always lies between -1 to +1. So what will be the range of R23 square? It will be between 0 and 1. Any square term always lies between 0 and 1. So what will be 1 minus of that? 1 minus R23 square. 1 minus R23 square will always lie less than 1. Right? It will be only a fraction. It will be strictly less than 1. So here you see, here from this particular thing, what you can say. The denominator is less than 1. So it is in the ratio form, 1 upon this. So you can consider 1 upon say half. So if you reverse this, it will be 2, which will be strictly greater than 1. So this expression will be strictly greater than, right? You can take any ratio, any number between 0, 1, you take here. If you reverse this, it will be strictly greater than 1. So what we get here is that we get that variance of alpha to cap upon variance of beta to cap is strictly greater than 1, which basically implies variance of alpha to cap is strictly variance of beta to, where what is variance of alpha to cap? Variance of alpha to cap is simply the incorrect model variance. Variance of the incorrect model. Variance of the incorrect model. So it will be strictly greater than this, which is the variance of the true model. And this basically proves you that the variance that you will obtain from the incorrect model, they will be inefficient in nature. Variance is greater Variance is greater in case of the incorrect model, which basically tells you that the variance of the estimators, variance of the estimators of the incorrect model. Incorrect means overfitted model. Incorrect model will be inefficient, right? They will be inefficient in nature, and that is what we wanted to prove, right? They will be inefficient in nature, and this is the last consequence that we wanted to prove. So whenever we consider hypothesis testing and confidence interval, we need to consider this also into account while before going into the hypothesis testing and the confidence interval, right? So overall, if you want to compare between the two things that we have done so far, suppose here I write the inclusion of variable and here I write omission of variable. These are the two things we have covered so far. So in case of inclusion of variables, the estimators are unbiased and estimators are consistent, right? But here it is not unbiased and it is not consistent, right? This is one of the consequences. The second consequence regarding the variance will be inefficient, variance will not be the smallest. Variance will not be the least, so it will be inefficient here. And here it is efficient. The variance of the incorrect model was lower than the variance of the true model, so that is why it is efficient in nature. Here the confidence interval and the hypothesis testing is valid. Here they both are not valid. And the fourth point that we can see, what will be the fourth point? What will be the impact of the degrees of freedom? Degrees of freedom. Since we are including more variable, degrees of freedom will be lower, and here if you are omitting the case, degrees of freedom will be higher in nature, right? So these are the comparative studies that you can do between the two things. Overall, if you see, overall, if you want to compare these two, you will say that inclusion is a better specification error. Better means the severity is less. Better in the term that severity is less, but omission will give you severe consequences. This is better, this is less severe, and omission is very severe, because see, everything is definitely a bad consequence except this, and here everything is a good consequence except this, right? So the proportion of bad consequence is more here than the proportion of bad consequence here. That is why omission is a more dangerous thing than the inclusion of variables, right? So yeah, that is all from my side in this video. I hope you like this video and get some meaningful things out of here. If you do, don't forget to subscribe to this channel in Economist. Please give me a like. I put in immense effort to make such videos for you every week. I try to post 2 to 3 videos every week, and it takes a lot of time. So all you can do for me is to subscribe to this channel and hit that like button. That will help me to grow my channel and also to continue making such useful videos for you every single week, right? So thank you so much for your time, and let's meet you in some other video.